Hey guys, this is a video for the third SI session, held January 30th. So in this SI session, I focus on radical reactions. So let's begin. So radical reaction number 1, we have this group. Oops. For some reason I can draw up there. Let me go down a little bit. We have this molecule, and we're going to treat it with CO2. So what's going to occur if it's only CO2 with no catalyst is that you're going to get no reaction, right? But when you treat the same molecule with CO2 and light, for example, or with heat, for example, then you get the following. CH3. So you were saying 3 of these hydrogen molecules, and then the 4th hydrogen molecule is going to be connected to a chlorine, right? So radical reaction. Alright. So for the next one, we have butane with CO2 and heat. And we're going to try to determine the 3 major products. So the first one is going to look like this, right? At this carbon right here. Second one is going to look like this. At this carbon right here. And then this is going to have one enantiomer, right? And that's the other product. The enantiomer is going to look something like this. Alright. Okay. With the same molecule of butane for problem number 4. Except this time we have Br2 in heat. And so something important to note here is that while chlorine is non-selective, Br is selective. So in the last example, we had chlorine create these 2 molecules. Oops, drew that twice. You know what? I'm sorry, I've kind of messed up. Right? Well, this is going to be about 40% yield, 60% yield. But with bromine, you're going to have the following molecules. Where this bromine on the right is going to have 98% yield, and the bromine on the left is going to have 2% yield. In that sense, bromine is more selective and going to choose the more substituted carbon, which would be carbon right here, as opposed to the primary carbon right here. All right. So problem number 5, let's draw all of the products. We have CO2 and light. So right now we can see that we can draw one hydrogen coming off from here, one coming off from here, one coming off from here, and another coming off from here, right? So we have 4 hydrogens. And which one of these, if replaced with the chlorine, would give us a chiral center? It would not be this one, right? It would not be this one. It would not be this one. But if you replace this hydrogen with the chlorine, you would get a chiral center, because you have one methyl group going off and then one isopropyl group going off. Your chlorine and then the other hydrogen that isn't drawn, giving you a chiral center. So from here, we know then we can start from that chiral center, right, plus an enantiomer. So that's 2 products. And then we can draw the third product, the fourth product, and the fifth product. So you may be asking, why are we not going to draw hydrogen from this one right here, right? Well, reason being that a hydrogen on that carbon right there is going to be the same hydrogen as the carbon over here. The exact same thing. Okay. Alright, so now we're going to draw only the major product for this same molecule, except we're going to be using Br2, right, with its catalyst. And so again, we can draw in the hydrogens. One hydrogen from here, one right there, one right here. So we can see which one might be displaced. And we know that Br2 is more selective than chlorine, so it's going to pick out the carbon that is most substituted, which turns out to be the carbon with this hydrogen, right? So we end up with the following product, Br. Okay, now problem number 7. This reaction uses concepts learned from Orgo 1, right? So we have the Br2 with its catalyst, can pick out any of the hydrogens. Let's say it's going to pick out this one right here. And we're going to end up with this, right? And then we can get a base. And what is the base going to do? Well, let's think back and realize there's a hydrogen right here. Or actually there's two hydrogens right here. But the base only really needs one. The base is going to do the following. It's going to get one of these hydrogens and do an elimination reaction so that this bond right here goes back right here, and the bromine acts as a leaving group and leaves. So now we did an elimination reaction, and we're left with an alkene. Okay, so for problem number 8, we're going to draw all of the products for this right here. And so I'm co-opting this exact problem from Dr. Plummer's notes. And the products would be they would look like this. The bromine right here, the chlorine right here, plus it's an enantiomer, and then the bromine right here with the chlorine right here, plus it's an enantiomer. So right there we have 4 products, and then the 5th product looks something like this. Oops. And then the 6th product looks something like this. Right? So these first 8 problems were radical reactions. Kind of an overview and non-specific. The next problems are more specific from reactions from lecture or concepts learned in lecture. Right. So we're going to have the following. Oops, it's supposed to be a 9. And 10. Right. With HBr with no catalyst, and then HBr with a catalyst. So in number 9, HBr is going to add in a Markovnikov fashion to the more substituted carbon. Carbon right here. In number 10, this catalyst right here is going to induce Br, or is going to induce this reaction to undergo a radical mechanism. And this will be explained more in depth in problem number 18. But for right now, we can just say that this is going to go in an anti-Markovnikov fashion and add on the Br on the less substituted carbon. Okay. Now we can do 11 and 12. So we're going to have the same reactant in 11 and 12 as we did in 9 and 10. We have HCl, and then we have HCl with its catalyst. So in number 11, we're going to have the chlorine add in a Markov-Nikov fashion. And perhaps for number 12, we're thinking that it's going to also add in an anti-Markov-Nikov fashion, just like number 10 did, right? But in this reaction, chlorine is actually going to add in a Markov-Nikov fashion, no matter this catalyst right here. So, oops, that was a mistake. So, oh man. What about iodine? So again, Markov-Nikov fashion. And even with this catalyst, Markov-Nikov fashion. So now if we look at all of these reactions together, right, you can see that only the bromine with the catalyst is going to add in an anti-Markov-Nikov fashion and undergo a radical mechanism. Right? Okay. So that's an important concept to note. So now we can go ahead and do some other reactions. So we have reaction number 15. Have this ring right here. And we have Br2 with heat. So let's start off from a reaction that is very similar without the heat. We know what's going to occur is that this is going to form an intermediate with a bromine bridge, right? And then the other bromine is going to attack, and we're going to be left with this enantiomer, or the other enantiomer. Doesn't really matter. But when you have heat right here, this is going to cause the PR2 to undergo a radical mechanism. So what actually ends up happening is that you retain your double bond, but you gain a BR, right? So let's go down number 16. Number 16, we have the following molecule. And NBS in light. So NBS in light, we've learned from lecture that undergoes a radical mechanism to produce its products. So we're going to be left with a similar product as in problem number 15. We're going to retain a double bond and then just gain a Br right there. So if we look at these together, very similar products. Right, adding a Br to the allylic carbon right there, and adding a Br to the allylic carbon right there. So, real quick, what is an allylic carbon? Okay. In this case, an allylic carbon is one that's adjacent to a double bond. So it'd be this one, and this one right there. Right? It's just adjacent to the double bond. So in this case, right here, and right here. Alright. So for the next problem, keep in mind that bromine is very selective, or it's more selective than chlorine, right? And keep in mind also that benzene rings are very stable. So benzene rings are not going to be messed with in this following reaction. Jeez. So we have number 17. We have this benzene ring, and the benzene ring can also be drawn like this. Conjugated double bonds. We have an ethyl group, and then we have an isopropyl group going off. If we treat this with MBS, what is going to be their products? So we're going to have two different products right here. One's going to have the Br on the tertiary carbon, because this carbon right here is tertiary. And then the other is going to have the Br on the secondary carbon, because this carbon right here is secondary. And then this is going to have one enantiomer, right, where the bromine right here is just dashed instead of a wedge. Okay. So next I'm going to get into mechanisms. So in this mechanism, I'm going to try to draw it more carefully than I've done before, but we're going to have this propyl group, CO2, and light. So we're going to have our 3 steps that we learned from lecture. And then the CO2 we can just think of as looking something like this. right? And we're going to go a homolytic, we're going to undergo a homolytic bond cleavage, like that, with a little half arrow. So our products are going to look like this. And of course, we can imagine our other 6 electrons right here, right? But usually, so I don't confuse myself, I just draw the radical and I opt out the other lone pairs. So you have those 2 radicals of chlorine. So for our next step, called propagation, what's going to happen is that you have this propyl molecule and you have different hydrogens right here, right? You have hydrogen number 1 and number 2. So chlorine is non-selective, so we can honestly pick out any of these hydrogens. So let's choose hydrogen number 1. So if it picks out hydrogen number 1, then what we have is this little half arrow, and then the bond right here, half arrow, and then a half arrow back to the carbon, right? And so what we end up forming is the propyl group with a radical, and then the H is going to be bonded with the chlorine, right? So in the solution, we have HCl, but we also have a lot of CO2, right? Which means that another one of the chlorines with the radical on it can react with this radical on the propyl group and form a bond. So that bond is going to look something like this. And so for our termination step, we can do this in multiple forms. So in the solution, we have the Cl radical, we have the propyl radical, and I can just draw another Cl radical right here, and another propyl radical right here. So this is about to be a little bit messy, but Cl radicals can terminate with this Cl radical, and this is going to form a byproduct, CO2, or Cl can terminate with this right here, which forms the product right here, or this propyl radical can react with this propyl radical, and we're left with the following molecule, right? So actually, let me draw that in green so you can see all the types of products that are formed. So all 3 products formed. Of course, you're going to want the monohalogenated product, which is going to be this one right here, right? Okay. So now we're going to draw the mechanism for NBS. We have this right here, and then this is straight from the problem that we did before. It is problem number 16. So we have the MBS, the light. So what's going to happen first? So what is NBS? We know that our product is going to look like this because we've done this reaction in problem number 16. But how do we get here? Right? So we know that initiation is going to occur first. Initiation is going to involve NBS. So NBS looks something like this. It has the bromine right here. And it's going to undergo homohaloic cleavage. Half arrow right here, half arrow right here. You're going to be left with a radical on a nitrogen. Oops, I forgot to draw the oxygen right here. And then bromine with a radical on it. So in the propagation step, you're going to have your bromine with the radical on it. And then you're going to have your alkene. Right? So in this reaction, we have two allylic carbons. One right here, and two allylic hydrogens. So we're going to pick any of these. For this one, let's say I pick that one right there. And what's going to happen, let me not draw this in blue. What's going to happen is that I have a homolytic bond cleavage. This goes right here, and this goes right here. And so we're left with the following products. HBr. And then we're also going to be left with the alkene molecule with a radical. And then, like we've stated before, there's going to be many of these Br radicals in solution. So we can just do radical reaction here, half arrow here, half arrow here. And so we're going to be left with the following product. Oops, that looks more like a pentene. Be left with the following product. Right? And so for the termination step, as before, we have the bromine radical in solution. We have the NBS radical in solution. Right? And we have the alkene radical in solution. And so any of these can react with each other to terminate. So let's just say this one with a radical reacts with another bromine with a radical, and we just get Br2, right? Or if you want to have this one react with another alkene, I can do that. And I'm not going to draw this product because it's not really necessary. Alright. And so next we're going to go over the last mechanism before we get to a synthesis problem. Alright, almost done erasing. What the fuck? Okay. So, problem number 20. We're going to have the same reaction that we did for problem number 10. And it's going to go through the same steps, right? So we know that radical mechanism can be split into initiation, propagation, and termination. So we can draw those out. And then we can have this ROOR homolytic cleavage first to give us this product, right? And then we have the HBr here. What's going to happen, oops, I meant to draw that in blue, is another homolytic cleavage, right? And we're going to be left with the bromine radical. And again, we can imagine the hydrogens in this molecule. You know, there's hydrogen right here, hydrogen right here, hydrogen right there, hydrogen right there. Right? So, what's going to happen here is that the double bond is actually going to participate in this radical mechanism. But let's think back on the stability of radicals. We know that tertiary radicals are more stable than secondary radicals, more stable than primary radicals, right? So it's going to want to take out, or it's going to want to leave the radical on the most substituted carbon. And if the double bond participates in this mechanism, then it means that only these two are left. So which hydrogen is more substituted, and where is the radical going to end up? Right. Hydrogen right here. So we can draw this mechanism now. And we can see that the double bond participates in this mechanism. Homolytic bond cleavage right there. And then the radical is going to end up right here. So the products that we form look something like this, with the radical right there. And now let's remember that we have the HBr in solution. And let's draw it out. This can go homolytic bond cleavage. And this can react with this radical. So now we end up with this molecule, and then the hydrogen, of course. So termination can occur in a lot of steps, as we've discussed before, so I'll let you figure that out. Okay, so for our next reaction, we're going to do one synthesis and see how that works out. Right, we're going to see how that works out. Oh shit. Sorry for the cursing. So we have the same reactant from problems 9 through 14. But we want to make the following product. So you can pause the video and figure it out before I solve it. But what I did is I added BR2, right, for medicinal dihalide. And then get a bulky base, 2 equivalents of it, to do elimination reaction. And we're left with the following molecule, right? And we can just do NaH or NaNH2 to give us an acetylide anion. So actually, let me draw this out. I'd rather draw it out. NaH, we're going to have an acetylide anion. And then we can just get acyl halide. Looks something like this, right? So we know that this reaction is going to proceed like so. React at this carbon, leaving group leaves, and now we have added 3 more carbons to give us this molecule right here.